Okay, since welcome back everyone. Since it has been a few days since we started current and resistivity, I would like to just review what we know so far. What's the definition of current? Charge per unit of time, right? So let's start with some review. So I is current, right? This is current. And it's dq dt. Units of current are what? Charge over time, coulombs per second, which is also known as an ampere, right? Amperes, yeah. Okay. So I will not write those. I will just say it. So that was the current. And then we had J, the current density, right? Current density. Current density. It was the current over area, right? Then we started, we talked about a wire of cross-sectional area A. Or cross-sectional area A. And then this is the wire. And we had charges moving across the wire. So let's say I start timing the charges as they pass by here. The first charge that passes at t equal to 0, and then after time delta t, that first charge will not be here, it will be here. And the last charge will be here. So this many charges have passed by. This distance is delta x, and it's equal to the average speed of the charges as they move, called the drift speed, Vd, times the time. Distance is speed times time. This is called the drift speed system. Drift speed, that's delta x. The cross-sectional area is A. And we asked how many charges have passed by. Well, that's delta Q. And that number of charges will be the number of charges per unit of volume. The number of charges per unit of volume, little m, which I have written there. And is, for example, silver, it's 5.8 times 10 to the 28 per cubic meter. So it's a large number, little m. Times the volume. This is per volume, so times the volume, that will give me the total number. And so the total number would be, the volume is the cross-sectional area times the distance, which is V d times delta t. This gives me the total number that passed. And then if each charge carrier has charge Q on it, which we will restrict ourselves to be just E. So I would just write that E is going to be little e. So that's the total charge that passed within the time delta t. So the current, I'm going to write it as this, delta Q over delta t is going to be little e times n times a times b d. Divide both sides by area, you will get your J. This, and we did even more last time. Then we talked about the charges as they, when they are in a wire. Why do they move? First of all, if I just have a wire, will I have a current? Yeah, a wire standing by itself, there will be no current, right? Yeah.
What's the variable e in this case again?
E, little e?
Yeah.
Yeah, little e is the charge.
Charge.
It's, So why would charges, let's say, move this way? Somebody has to apply a force, right? to them. And that force would be from an electric field. Somebody has to apply an electric field. So let's say we have a charge here, a positive charge, and apply an electric field this way. And so it will feel a force in that direction, right? It will feel a force in that direction. So the force on a charge is the charge times the electric field, right? That's the force. And Newton's second law says the force is equal to mass times acceleration. So the acceleration will be little e capital. That's the acceleration of that charge. So from kinematics, we know that velocity is equal to v initial plus the acceleration times the initial times acceleration. Right? This is from mechanics. Right? And we're going to substitute for the acceleration, all that stuff. So we get v is v naught plus e over root naught times the electric field times v. Now, I'm not interested in one charge, how it moves. I'm interested on average, how do they move, right? Because do we have just one charge moving? No, we have 10 to the 28, right, per cubic meter. So many more than just one charge. So how do they move? On average, I need to average. So what's their average speed? So that we'll take the average on both sides. It's just going to be the average. So that remember when we put brackets, it means average. So like this. Why are these not average? They're constant, yeah. The average of a constant is itself, right? The average of the number 2 is 2. So, now these have different averages. Now, what's the average initial velocity? It's 0. And why would it be 0? It is 0. Initially, in what direction are charges moving?
No.
They are moving in random directions. They could be moving left, right, up, down. They're colliding with each other. So initially, after every collision, a charge might be moving backward, and it might be maybe somebody hit it from the back, it might be moving forward. It might move up or down. So on average, it will just be 0. So this part is 0. This average velocity is the drift speed. That's the drift speed. And I'm going to drop the vectors because I want their direction would just be the same as the direction of the electric field. Right? This vector's direction is the same as this vector. Same as the vector. T, so it will accelerate and then collide, and then accelerate again, and then collide. So t is the time that it accelerates freely, right? So it's the time between collisions. So t is a measure of how long it will take before it collides. So if t is long, it would go for a long time before it collides. So if t is big, the average drift speed would be larger. But if the collisions are very frequent, then the time will be short. So the average time here is called tau. We're not going to do much with it, but it's called tau. In fact, I'm going. Let's just write it here. That's tau. So I'm going to go back to here and write J, but instead of V drift, I'm going to substitute this stuff. So here's J. You will have E times N, but then I have E comes from here. So I will have E times N, it would be E squared, right? So it would be E squared times little n times tau over N, and then E. That's the electric field. Okay? Let me make sure I got it right, and you forget anything. Yeah. So this combination, this is a constant, this is a constant, depends on the material. Tau also depends on the material, frequency of collisions. And M also is another constant. So all of this is a constant. And it has a special name called sigma. And that sigma is not, well, let me write it. So all this is called sigma. You get J is sigma times the electric field. This is called conductivity of the material. So sigma here, so yes, we used the symbol sigma before, but this sigma doesn't mean what that other sigma meant. That other one was the charge density, right? Surface charge density. This one is the conductivity. Okay? And then we can solve for E in terms of J and then get another term. So if we solve for E in terms of J, we get this. E is equal to 1 over sigma, right? Times J. So E, what do you think the inverse of conductivity is? Up to some resistivity. Yeah, resistivity. It will be related to resistance. So 1 over sigma is called resistivity. So it's rho times J. This is called resistivity. We will talk about its units in a moment, but for now, resistivity, if you have a conductor, resistivity would be very low. Right? If it's a conductor, it should have low resistivity. If it's an insulator, resistivity will be high. And I have the numbers there on that board. You can see it with the camera, I guess. But I would just say, for silver, resistivity is, don't worry about the units for now, we'll talk about that. Resistivity is something times 10 to the minus 8 for silver. And for aluminum and iron, all of them are something times 10 to the minus 8. Tiny. Resistivity is small. For insulators, their resistivity is what? 10 to the 14. Right? Compare 10 to the minus 8 versus 10 to the 14. Air, 10 to the 16. And then you get, so different things, they have different resistivities. So for conductors, very low resistivity. Insulators, very high resistivity. And the range is high. From 10 to the minus 8 to 10 to the 23, we're talking like a range of 10 to the 30, right? It's a very large range. So it's clear what a conductor is, and it's clear what an insulator is. Their orders of magnitude is very immensely. Resistivity is a property of the material. Conductivity is also a property of the material. They're just reciprocal to one another. And you look it up, and then you find it. Just like density, you just look it up, right? And so mass is not a property, right? It's not like an intrinsic property of the material. I can get more water, I can get more mass. But the density of water will just be the same. By the way, this and this, it may not be obvious or in the most familiar form, but if you have seen Ohm's law before, this is Ohm's law. So let's make it look more familiar. This is called Ohm's law. Yeah?
And could you back when you compare it to J, how do you get sigma again? Or what did you call it?
We just named all this stuff sigma.
So did you derive that or did you just put that?
Did I derive? So this all this combination of letters is called sigma. Just name it.
How do you know that in your water your electric field is constant?
You're applying some constant electric field. Yeah.
Is it usually constant? Because
If it's the same material, it will be constant. We will. Yeah, go ahead.
so if like the wires are made out of like 100% copper and all you have is a battery and a capacitor, and the capacitor isn't there yet, then it's constant.
Yeah, the electric field more or less will be constant. Unless you change the material, then the electric field inside that material might change. So
The wire is a conductor, copper is not electric field.
it's a good question. Yeah. So Jasmine, she's saying the wire is a conductor. So why is there an electric field inside it? Yeah, that's a good observation. What do we say? Huh? Inside. Yeah, there is an electric field actually inside. What's the difference? Huh? Yes. First, the difference is we're not electrostatics anymore. Charges are moving in this case. That's the first one. Secondly, when we talked about the electric field being zero, it's a perfect conductor, right? A perfect conductor will have zero resistivity. These are not quite perfect. Yeah. So you would need a tiny electric field to cause the charges to move. So good observation. Yeah. So two reasons. We're not in electrostatics anymore. Charges are moving. The other one is we're not they're not perfect conductors. And so as you can see, that's like I'll come back to it.
Okay.
Yeah, maybe. Yeah. Basically, the electric field or resistivity is a measure of how much electric field do I need to drive a current. And if this one becomes close to zero, I need almost zero electric field to get a current going. Yeah.
But any chance, does the voltage of the battery supply also create field?
That is the electric where the electric field comes from. Yes. Yeah. Yeah. Okay, so we got to that. Before we do any examples, let's continue with this. So now let's consider, here's the wire. Here's the wire. And here's the electric field. Let's say the electric field is to the right, and the length is L. This length is L. What's the potential difference across? First of all, is the potential, let's call this point here B, and this point here A. Is the potential at point B higher or lower than point A? At B or A? A point is higher. A is higher? Why is A higher? You have to give me a reason.
Because
That's further to go. Yes.
working contrary.
Yeah, think of the infinite plate capacitor, infinite sheets. Plus sheet, negative sheet. The electric field is this way. If you go from the negative to the positive, you go to higher potential. So when you go with the electric field, you always go from higher to lower potential. If you go against the field, you're going to a higher potential. Just like gravity, it's down, right? If I go with gravity, I'm going from a higher to a lower potential. So yeah, so point B has lower potential than point A. But what's the potential difference between the magnitude V? Potential difference, which is, let's call it basically VA minus VB. What would it be in terms of the electric field and the current?
EL.
Just EL, yeah. Yes. Yeah, it is EL. Good. The electric field times the length. Yeah, it is EL. Right? ED. For parallel plate capacitor was electric field times the distance between the plates. In this case, I'm calling L. So let's look there. So we get D is equal to E times L. But E is rho times J. So rho times J, rho times J times L. But J is I over A, right? It's current over area. So I have rho times the current over the area times L. So then I get V is equal to rho times L over A times I. Okay? Yet again, we have another letter that we're going to meet. All this is going to be called R, resistance. All this is in the box. The R is resistance. Resistance. So it's time to talk about the units. So R is the resistance. Okay. Let's talk about the units. Yes. Units. Let's start with R. The units of R will be V over I, right?
Yeah.
V over I. So it's volts per ampere. It will be volts per ampere. And 1 volt per ampere has a name. It's called an ohm. 1 ohm. And it has an abbreviation. Looks like this. Capital omega. So that's the symbol for an ohm. This one we haven't encountered this symbol before, so there is no confusion with this symbol. So that's the unit. Those are the SI units for resistance. How about for resistivity? Well, let's say resistivity. It will be. Let's solve for resistivity in terms of R. R is rho L over A, so rho will be R times the area over L, right? The area, the cross-sectional area of the wire times the length of the wire. Now, what are the units of A over L? Meters, right? Square meters over meters is meters. And this one is ohm, so the units are going to be ohms times meters. So the units are going to be ohms times meters, which is what I have over there. If you look at the board, ohms times meters for resistivity. Sounds good? And this thing here is more known as the more known form of Ohm's law. We will use it when we do circuits. Okay. Time for some examples. Just to make sure we got everything. Unfortunately, I wrote only on these 2 boards, and the examples are on the whiteboard below, but I will lower it. Let's start with the first example. I have a 2 millimeter diameter aluminum wire. I'm telling you it's aluminum, so we can freely look it up, what we need for aluminum. It carries a current of 800 milliamperes. Find J and E. Find J and E. So what can we say about J? I over A, good. It's the current over the area. And the area is the pi r squared, right? Because the diameter of this wire is 1 millimeter, so we can find the cross section. So it's I over pi r squared, so I get 800, or not 8, 0.8, right? 0.8 amperes, 0.8 amperes, and then pi times, the diameter is 2 millimeters, so the radius is just 1 millimeter. So 1 times 10 to the minus 3, because we need it in meters. And then you have to square it. My fraction didn't go. Straight. I'm sorry? The radius, right? Yeah. I really should. Oh, I don't have it actually. I need notes for this one. It should be large, right? Something times 10 to the 5th, probably.
From where did 0.8 come?
800 milliamps is 0.8 amperes. Divide by 1,000. So it'll be something times 10 to the 5th. Amperes per square meter, right? What's the number here? Anyone?
2.55 times 10 to the 5.
2.55? Thank you. 2.55. All right. Next is the electric field. What can we say? Yes. Resistivity times J. Is it too small? Yeah, can you see it? Oh. So resistivity times J, right? So rho J. Rho times J. Okay. Rho, you need to look up aluminum, right? So aluminum, I wrote it on the board. It's where is rho? 2.65 times 10 to the minus 8, right? So 2.65 times 10 to the minus 8. And then J is this, 2.55 times 10 to the 5th. So we got our electric field. I have 0.0067 newtons per coulomb or volts per meter, right? Both are units of the electric field. So that's the electric field. Next example, more of a conceptual one. Next example. Next example, you have two wires. They're made of the same material. Same material. If they're made of the same material, do they have the same resistance or the same resistivity? Resistivity, yeah. Resistivity is the property of the material. Resistance depends on how long and how wide the wire is. Okay? Just like density and mass. Okay? So they're both made of the same material. This one has radius R1, and this one has length L1. However, R2, this one is length L2, and L2 is twice the length of 1. And then R2 is twice the radius. R2 is twice R1. So the bottom wire has twice the radius and twice the length. And the question is, what's the ratio of their resistances? R2 over R1. Let me write it here. Remember, resistance was resistivity times the length divided by the area. Okay? Increasing the length, does that increase resistance or decrease it? If you have a longer wire, it gets larger. Yeah. How about increasing the area? Yeah, less resistance, right? Yeah, less resistance. So wire 2, we doubled the length, so we increased the resistance, but we made the area bigger. By what factor is the area bigger? By a factor of 4, yeah. The area is larger, right? It's 4 times. You double the radius, you make the area 4 times as big. So which one do you think would have the larger resistance, 1 or 2? Yeah, 1 would have the larger resistance. So R2 over R1 would be less than 1. It would be a half. So let's figure it out. So R2 over R1. Let's see what we got. You'll have this. R2 would be rho L2 over A2. And R1 would be the same rho because they're made of the same material, but L1 over A1. Yes? So rho cancels. And I have L2 over L1 times A1 over A2. That's what we have. So we get R2 over R1. L2 over L1 is what? 2. Yeah, L2 is twice L1. So the first one you get 2. How about the areas? Ratio of their areas. A1 over A2. It's 1/4, yeah. Because you double the radius, you quadruple the area. So area 1 is 1/4 of area 2. And so you get a half. So the ratio of their resistances is a half. R2 is half of R1. If R1 is 10 ohms, R2 is going to be 5. Half. Next example. I have it here. Next example, very similar to this, but not the same. So we have two shapes, two objects made of the same material. So again, same what? If they're the same material, same resistivity, same rho. Both of them, the current flows upward. So this one, the current flows up, and this one, the current flows up. Both of them. Okay? The resistor on the left, this one, R1, has a resistance of 1 ohm. The question is, what's the resistance of this one, R2? What would it be? What would be the resistance? How much? Is it going to be 1 ohm? Is it going to be 2 ohms? Is it going to be less? More? So how do we figure it out? Any ideas? Set their the resistances, resistivities. Okay. That's a good idea. Okay. So here's what we know. Relation between, since I have the entire thing right here, R1 is going to be rho times L1 over area 1, right? So I have rho. What's the length of this resistance? R1. For this one, what's the length? Good. Yeah, the length is this one, right? The length along which the current flows. So it is 50 millimeters. Is that clear? For this one, the length is 50 millimeters. So we got 50 millimeters. Actually, I will not substitute the numbers yet. I will just do this. Rho would be R1, area 1 over L1. Okay, I'll just do that. I will substitute the numbers in a moment. Similarly, R2 would be rho L2 over A2. And so rho is R2 A2 over L2. There. Now, they have the same resistivity, so we're going to set them equal. So this must be have the same resistivity. So we're going to say R1, A1 over L1 is equal to R2, A2 over L2. That means R2 equal to R1 times L2 over L1 times A1 over A2. I'll wait a moment to make sure that we're all on the same page. Any questions on what I have done so far?
So can you take the area of
So now it's time to substitute the numbers, okay? So let's substitute. So what is R1? 1 ohm. L1, I'm sorry, L2?
75.
L2 is, yeah, it's this way, so that's the length, 75.
Over 50.
And by the way, there is no reason to convert to meters. Everything is going to cancel, all the units. L1? 50. Now, area 1.
50.
It's
100.
100 by 20, right? So, okay, 2000? Okay, so I would write 100 times 20 and then, so 100 times 20. And then this area, 50 times 40. I would write this 50 times 40 first. And you're right. 2000 on top, 2000 on the bottom. So the areas, these numbers cancel. Okay. And so you just have 75 over 50, which I think is 1.5. 1.5. So you just got 1.5 ohms. So 1.5 ohms. So that's the resistance of that one. Obviously, wires don't come in this shape, right? But this is just for practice. Let's do another example. And then we will go, only need 2 more examples. Let's see. Then we go on to the next chapter. So the next example, I have a wire of variable resistivity. Resistivity is not constant, it's variable.